Yeah, I have the honor to do the last talk of the technical program before the panel discussion. Yeah, so my name is Daniel Arndt, and I work mostly on Kokkos, and today I'm presenting on the experiences we had with implementing Kokkos SYCL backend. So what is Kokkos? Kokkos is a similar approach as Raja, basically a C++ programming model for performance portability, and we have multiple backends, originally starting with like CUDA and OpenMP, Serial, and all that kind of stuff. Originally developed from Khronos, but now joining the Linux Foundation, and thus just like very independent of any particular institution, although mostly developed at the national labs in the US. We always try to play a good role in promoting features that we think are useful for the general C++ community, like DMD span, which primarily developed or prototyped by Kokkos developers, Atomic Graph, and then also the std-lin alg. We have a little bit more than just like the core functionalities, but also math libraries, some tools, and interoperability. So we kind of try to found like a total ecosystem for users to use, particularly in the HPC community at the labs, driven by the labs mostly. It's open source, so feel free to contribute. So this is a little bit what the Kokkos ecosystem looks like. Like we have on the right some support. We do all kinds of bootcamp tutorials, documentation stuff. What I'm focusing today on is this here in the middle. It's Kokkos core. They basically just doing the basic blocks, like some parallel constructs and policies and all that kind of stuff. We have some more support in libraries than for, say, SIMD types. Or parallel algorithms is also something we just implemented, and also like within kernels with some more efforts with PGAS, remote spaces, Kokkos kernels on top for linear algebra, which goes in the direction of std-lin alg, of course. And then to the left, all kinds of tools so built in the Kokkos system that you can use to debug and profile kernels. The Kokkos applications make these days out like 50% or something like that of all the exascale computing projects. So that was like a big success for us, that it was very widely adopted, in particular since we have like Khronos and Patsy on there jointly that were somewhat like more competitors, historically speaking. And then some more applications here with final element stuff. We heard from LAMS, XGC is using it. Yeah, VTKM, Uinta, all kinds of things. Also at Argonne Labs here. The feature status here is basically that it's very complete, except for some features that are not really users don't really use. Which is any kind of tasking or graphs or work graph policy. So any kind of tasking is basically nothing that people ask for. So at this point, we are looking into also adopting SYCL graphs, as command graphs, the extension in the DPC++ compiler. Just similar to CUDA graphs and the other ones. We'll see if we want them depending on what users ask for. One thing people ask for is virtual functions and function pointers, but this is nothing we can do about it. I know, I mean, there's some effort, again, in the DPC++ compiler to support that. And we'll try to support that. We'll see if we can introduce more syntax. Okay, but then maybe just back to the basic functionalities that we provide and that I will discuss a little bit here. We have a parallel 4, which just maps to a parallel 4. We have a parallel reduce and a parallel scan, and these are like the 3 basic blocks. And as you can see here, we don't really use any kind of reduction variables, or at least that's what I wanted to express here. We just use parallel for all of them, and then just implement all of these things our own. In terms of policies, we have a range policy, which is supposed to map to like simple ranges. So SYCL ranges is very natural coming in here. We have MD range policy, which describes the multidimensional range and also provides some support for tiling that naturally maps to ND range, and then team policy that describes hierarchical parallelism. And we also map that to ND range directly, and we don't use the hierarchical parallelism constructs in SYCL, and we'll discuss that a little later. For the memory, our primary construct is a view, and you can think of that basically as a wrapped MD span wrapped by a STD shared pointer. So you have like all kinds of memory management with that, and we map all the SYCL memory spaces in there, all the USM spaces. So like host, pin, shared, and this device. Okay, so let's see, how does that really look like? For range policy, parallel for very easy. So what we're just doing is the user has some kind of functor somewhere, just we write that here as a lambda, basically, and then that kind of exists in the implementation outside here, and then we just call range policy begin and end. The shift thing got deprecated in the SYCL standard at some point, so we need to shift our indices explicitly, and then we just call the functor. Very straightforward. But if we now look into maybe just using IOTA, something like that, we run into a couple of problems or discover a couple design decisions, let's say. Yeah. So basically, this approach already shows that using SYCL buffers is not really viable here. Because we have when we map our views, there is no point where we can put in accessors, since that's like transitively managed in the kernels. So USM is really the only option that we have, and it works well. Then just for a simple kernel, we run into problems with device copyability. Basically, we store like a string or something with the view, or in general, like user kernels are just not really copyable. It just works out of the box on other backends like CUDA and TIP and everywhere. So it's really hard for us to enforce like this device copyability. Okay, so what happens if we just say, hey, all views are device copyable, sorry. Well, the specifications say then it's up to the implementation, basically, if you really call the special member functions, like if the copy constructor behaves like a mem copy, or the destructor is actually called. And that poses problems. Like, it's not enough for us to just say, hey, it's device copyable, because implementations then really want to still use the member functions. And so was a really big hurdle for us. Yeah, you can see that in like this issue on Intel LLVM. Basically, and what we came up with is we define a trivial wrapper, basically. So we wrap our functor in a union, and that way we can just specify what the special member functions are that get invoked. So we really manually you do a mem copy and then say that the destructor is empty, and then everything is good. Then we can just say like this whole thing is device copyable, and then the implementations don't complain and try to do stuff that that other backends don't do. Yeah, you can see that here. Basically, we have the function wrapper, we have the union that does the functor, and then on the device, we just say get functor, so then we can really invoke that, and it works well. In particular, if we then just say is device copyable, that works. Okay, so from this point of view, range policy parallel for works well, everything is good. MD range policy maps up to 6 dimensions. In Kokkos, which is a little bit more than what SYCL provides. And I mean, these 6 dimensions is something that users really want. And something to note here is that this is always doing tiling, either like defaulted stuff, what we think is good, think of like a 2.5D implementation basically there. And yeah, we can just reuse the implementation here for CUDA and HIP that does all the tiling and mapping, and that pretty much just works out of the box. So we just have like a 4th dimension. We just match that with the first dimension, and nothing really to do here. That just works well. Team policy is then our version of hierarchical parallelism. We use like a 3-level parallelism here. So we have the outer loop, which just divides the execution space then and the iteration space in a number of teams. And then within each team, we have a team thread range, which defines a Kokkos thread. And that can be further subdivided in thread vector range. So basically, within each thread, we have some vectorization, if you think about like more of a host implementation, basically, but explicit. So we have like these 3 levels, and basically that does redundant execution like outside of the respective levels. So beginning of the outer loop here, you do basically redundant executions on all the Kokkos threads, and in the team thread range. Here in the beginning, in the middle body, you do a redundant execution on the thread vector range. And instead of these 3 levels, you can just collapse everything and have a team vector range. And that means just that you basically ignore this middle layer and then just like, iterate with all available parallelism. And this is a concept that works really well for us. And you can see that all this is nested, like the parallel constructs can be different in here. So we have a parallel reduce or parallel scan then on the respective levels. And you can also use like STD algorithms in there. That's also implemented, at least those that we implemented. Okay. This is the only policy that allows scratch allocations, and the way we map that in SYCL is basically say a team is a group, and then multiple threads are mapped to a subgroup, which is a little bit challenging because now we are dealing basically with synchronizing subgroups, like parts of a subgroup, since the vector length might be is user provided, right? I mean, so in a very simple case, the vector length would just be the same as the subgroup size. But if it's not, if it's just like if it's just a multiple, then we need to deal with that. And in the current implementation, that poses challenges since we need the synchronization here. And that works on Intel GPUs well because subgroup barriers are basically no-ops, but it doesn't on CUDA. And so to support that, we need something like tangle groups, but that is unfortunately not implemented for NVIDIA GPUs where we would need it. So that's a little bit of a problem, but since we are mainly targeting Intel GPUs, we are fine for now, but we are looking forward to just fix that as soon as possible. Further, I talked about scratch allocations, and our scratch allocation interface basically allows to provide different levels of scratch allocations, like you can access local or global space, but they kind of return the same pointer, at least, like in the interface level. And that provides a little bit, a few problems for the compiler. Like it's, in a lot of cases, not really able to figure out what we really wanted here. So we will probably try to have a separate interface there. And Yasi already talked about that a little bit, where they tried that out in LAMPS to some extent. And so then that should also go away. I mean, basically we say, yeah, we just have two classes for scratch allocations. One directly maps to local memory and the other one to global memory. So for the most part, this is also like a solved problem. Okay, so now we have all these policies. So we talked a little bit about parallel 4. It works very straightforwardly. For parallel reduce, we have the following interface, which is a little bit different from what SYCL provides. Basically, we just say parallel reduce, and we don't have reduction variables or anything like that. And then on the functor level, this is very similar what we've seen, I think, with Raja, where we have like a update directly on the specific value type. So in contrast to what SYCL is doing, we don't have like any reduction variable in here, which directly then does that. But it's driven from the outset. So you're supposed to just work with the value type here. And then finally, this local variable will finally be written to this result variable. There are some versions where you don't need to do that, basically because we are able to do some pre and post callbacks. So instead of just writing to a variable, you can just kind of register a callback there that does something else. Maybe just take the square root or something of the final result. And yeah, we support a bunch of different features. We can do multiple reduction. We can do custom reductions with arbitrary value types and reduction operations, runtime sized array reductions. And we decided for the moment not to directly use the reduction variables in SYCL. One of the reasons being that like SYCL 1.2.1 didn't support that interface at all, so it was not really available at the time we started doing this, but then also it's not quite clear if we can map all of this the same way. Like in particular, calling like this pre-callback init on each thread is not something I think would work. But we could see if we wanted to do that for simple cases where we know we can map. Okay, so the implementation is very straightforward. What you think it should be for GPU implementation in general. For anything parallel, we just initialize here with this init callback and the local value. Then we just do like a local reduction, and then we join. Calling join actually is a function in our reduces the values between the threads. And that can either occur like with shuffles or local memory. And then we have one work group that just merges all results from all work groups. And we all do that in one kernel, which is the implementation is basically, is very similar to what GPC++ would do on GPUs, at least for these kind of things. And finally, we call final on our result. And one thing we noticed is that the shuffle-based implementation gave us a little bit of a headache, since the performance was just not very great. Like other people have seen that, like the hack team or the Ember people. Basically, it's really crucial that you need to that you provide the information then at compile time. And with that, we were able to recover some. Okay, I think I need to speed up maybe a little bit. So let's see. The third construct we have here is parallel scan. A very similar interface, but we have this is final variable. Basically, we do a 2-pass implementation. So you're able to access the data in the second pass already and don't just have access to the final result as you would maybe have with STD scan or inclusive scan, exclusive scan. So you can do all that all in one go. You can do an inclusive scan, exclusive scan, all kinds of things if you want to. And we think this is a very important stepping stone. Okay, implementation-wise, this is similar to reductions, but it's a two-kernel approach. So on the first one, we basically do the scans for every work group, and then in the end, we just have the work group results and then merge them back. And here we always need to use a shuffle-based implementation. We can't just use local memory for that. Okay. With that, I want to come to some performance comparisons. Pretty simple. The ultimate goal is just to compare like a conjugate gradient solvers, and there are a couple ingredients we need for that. We need like a XPVY, a dot, and then a SPMV. And the results here were gathered on Sunspot with Intel Data Center GPU Max, also known as PVC. And the peak memory bandwidth is kind of what we're after here, is around 3,200 gigabytes with 2 tiles. So like 1,600 per tile. Okay, so the XPVY benchmark, very easy, is just that. We discussed before what that would look like in SYCL. No surprises here. And since it maps very easily, wow, okay. We see that the performance also is basically the same. It's quite interesting that we see here some caching effect just from probably running the kernel a bunch of times. And also we see that it really only pays off to use 2 tiles for like 1 million elements or more. But then we get like a factor 2. But yeah, it's more like an effect of running an Intel GPU, which is interesting because we typically get more out of the bandwidth here on NVIDIA and AMD GPUs. Okay, dot benchmark is just a simple reduction. Here we compare it with the reduction variables in SYCL. Actually, we use a USM-based approach and do mem copies, and that's what we also have in Kokkos from the behavior-wise. And again, results are pretty similar. Again, some caching effect. We see that the results differ a little bit. To dive into that a little more, we just plot here the ratio in runtime. And see that, yeah, I mean, we are maybe like 20% faster for like smaller workloads, and then the SYCL implementation is a little bit faster, but that should only be about like tweaking some work group sizes and all that kind of stuff. Basically, I would say it's also kind of the same performance. That works well. Okay, SPMV. For the SPMV, we actually use hierarchical parallelism, and we use some values that are optimized for the GPU here. So I manually try to optimize that. So we try to do like 32 rows per team, team size of 16 and the vector size of 4. As you notice, that is less than the subgroup size, 1/8. So we map then multiple of these Kokkos threads. Okay, conceptually what we're doing is we just divide our ranges over some teams, and then we loop here again with the team thread range. We get each Kokkos thread, multiple rows, and then in the end we parallelize with the vector length basically over all the operations we need to do here for the matrix vector product. So they happen in the innermost loop. Very nice. For SYCL, we just compare here with the parallel 4 work group, and then parallel 4 work item, otherwise the same. Here we are missing out on the third level of parallelism, so we just have a serial loop in here. And if we look at results, that turns out to be quite important in this case. So we have Kokkos here with the diamond shapes. We get consistent performance basically with what we are seeing before. Again, some caching effects here going on. SYCL just gives us like half of that performance with this implementation at least. And we also compare with 1MKL, which where we also perform better. basically for up to like a couple million elements, which is a little surprising to us. Okay, so the final implementation, final benchmark then is CG. I'll just skip through this since maybe you want to have some questions. Basically, this is driven. This is most of the time is spent in the matrix vector products anyway, which is why we expect similar results. Now we see here the caching effects are less pronounced. But again, the SYCL implementation gives us like half of the performance. And 1MKL also needs some time to catch up to that very simple implementation. Okay. So in a summary, we are like pretty happy with how porting went. It works well for us on Intel GPUs. It works way better than OpenMP Target, where we always have problems doing that. Yeah, it's easier to use C++ features. It's catching up very nicely there. And in general, we consider Kokkos to be like an extension to some extent of SYCL. If we just talk about the SYCL backend, where we provide multi-dimensional array accesses and then a parallel scan, and at this point, a better hierarchical parallelism. And we have a couple or more high-level data structures or capabilities like standard algorithms, but where Axel also said, like in the implementation, they're looking into that as well. But I think in general, this is something that users really need. And yeah, that brings me to the end. And are there some questions?
For the MD range policy, you said you map that to a three-dimensional ND range. So does Kokkos have to, which I guess you have to do for all of the backends, right? If you go to CUDA or HIP, you do the same thing.
Yeah.
How much of the responsibility does Kokkos take for making sure that you map those in a sensible way? For example, if some of those dimensions are pretty small and some of them are pretty big, whose responsibility is that? Is that Kokkos's or is that the users?
It's the users for the most part. Like, yeah, I mean, the tiling is something that we default to, but the users can provide. But we don't try to optimize on that. Like what we say, it's like the leftmost indexes should always be the fastest running one.
Okay, thanks.
Yeah, on a related question, you have no problem with barrier or something like that? If the guy or just want to wait on one of the barrier size or one of the dimension or something like that?
No, I mean,
Oh, you have no barriers, this is maybe.
I mean, we don't use, I mean, the user cannot provide any barriers.
Oh, okay, this is
like, this is only team policy where we have more control and
I
expose like more of SYCL's capabilities, if you want to say that. And then there we have issues in the deepest level where we want to only synchronize subgroups.
Thank you.